Greetings and welcome, friends. Mr. Waddy and my math friends in real life are here to talk about exponential functions. We're looking at last night's quest on page 310. 310. And here's some problems we're just going to go over real quick. It says, for this, determine whether the equation represents an exponential function. Explain. So exponential functions in general were of the form y equals a times b to the x. All right. And notice my variable x is in the exponent, right? Exponent. So the question is, do any of these match that? And so for the first one, notice a would have been the 4, b would have been the 7, and x is in fact in the exponent. So this is exponential. All right. The variable is in the exponent. This next one, what are our thoughts on question 7? Well, the x is not in the exponent, but an exponent exists? This is actually not exponential. Wow, I also forgot how to write over vacation. Exponential, because there's no variable in the exponent. I don't think you'll see what this looks like in this course, but that is a polynomial function. Specifically, it's a cubic, C-U-B-I-C, cubic function, third degree polynomial. And graphically speaking, it looks like some crazy thing like that. It's weird. So anyways, this next one, question 9, notice the variable is in the exponent. This is exponential. Exponential, right? So that's just a matter of, can you recognize an exponential function based on its equation? And I think we did okay. Here, let's take a look at this. Determine whether the table represents a linear or an exponential function. So we're going to take a look at the changes. So notice these are constant intervals for the inputs, the x's, right? The dependent variable. Those are all just plus 1, plus 1, plus 1. But now the question is, what's happening to the y? And so to go from 6 to 12, either it could have been plus 6, or it could have been multiplied by 2. Now, if it's just plus 6, that would be linear. That would be like the slope, 6 over 1. If it's multiplied by 2, that would be exponential because there's like a multiple between terms. So let's see which pattern works. So does 12 plus 6 give me 24? No. So this pattern fails. Is 12 times 2 24? Yeah, times 2. I agree. And is 24 times 2 48? Times 2. I agree. So this is an exponential function. All right, because there's this over set intervals, right? These were increases by 1. These could have been increases by 2. As long as these are the same, there was a constant multiple that I was dealing with, right? Multiples of 2, right? Or doubling the previous term, right? Instead of repeated addition or subtraction. Also, these could have been divide by 2s, and that also can work for exponential functions. Okay, here we go. Evaluate the exponential function. So I want to plug in 2 for x. And notice this is exponential because the variable is in the exponent. Also notice this little colon here. So you made sure that that wasn't all like part of one function. So y equals -4 times 5 squared. So I plug in 2 for the x, and according to PEMDAS, parentheses, exponents, multiplication, division, addition, subtraction, I would do the exponentiation first. So 5 squared, 5 times 5 is 25. And -4 times that, 4 times 25, we all know what that is. That's 100, and then throw a negative in front. And I get y equals -4. So to evaluate an exponential function, you just plug in for x and then use PEMDAS as it is appropriate. All right, let's see. The last question I'm going to look at here I actually gave myself a graph just a moment ago compared to the parent function. We won't tell our internet friends, but I think I ended up telling you guys you didn't have to do these ones, but we'll go over it nonetheless, because future generations of students will probably have had to do these. So let's see. It says graph the function and compare the graph to the graph of the parent function. So this parent function that I have here, this is y equals 8 to the x. And now the question I'm wondering about is, what does multiplying this by 1/2 out front do? And so what do you think it'll do? It makes it smaller. Like, in what direction? Like, so here's 1. Where would this new point be? Well, 1/2 of this, it's changing the output of the function by making it half of the original. So I would just take this, which is 1, and divide it by 2, and I'd get 1/2. All right. Here's a point right. Let's see. Oh, 8 to the x. Yeah. So here we go. So here's the point over 1, right? Up 8, and half of that value. What's half of 8? 4. So this would have been halved right there. I also could pick some other values here. So here was 2. It was over like 0.75 or something like that. Who knows? And what is half of 2? 1. So if I move this down exactly half as much, I would have landed there. Here was 4. If I move that down half as much, that would have been at 2. And even here, here was a quarter. Or no, sorry, a half, because this was 1, my bad. And half of a half is a quarter. So half that height, half that height, half that height, right? And my graph, let's see how well I can draw this. Nope, I went under the something like that, right? Yeah, it's I would have had like half of 64 is 32. So yeah, so what I end up having is a graph whose y values are half as much as the parent function. And so to describe that, I could have said this was a vertical shrink by 1/2, right? Because it shrunk it in the y direction. All right? Okay, so thanks for watching, internet friends. Have a good day.